Let's get to it. Okay, so let's go ahead and get started on limits again. Again, the idea of limits is what should it look like? And that gives us a lot of freedom because in many cases, we don't know what it looks like. As an example is, if I write the example of f of x is 1 over x, and I ask you, what does the graph look like at f at 0? And if I try plugging 0, we end up with something called undefined. So using direct substitution by just plugging in a value, it didn't tell me anything. Right? You ask the question, it says, I don't know. We know that it doesn't exist there. The graph looks like a graph that shoots off to infinity. But it shoots off into infinity in different ways. Like on the right side, here, it goes to positive infinity. On the left side, it goes to negative infinity. So we have ways of describing different sides of a limit. And we call that our left and right. So the left limit and right limit. We talked about this yesterday, that instead of just saying, I have no clue, it's undefined, it's a lost cause, we could describe this as the limit as x approaches the number 0 from the plus, the right side of 1 over x. So as I'm approaching from the right side, we can now describe it as I get closer and closer and closer to x is 0, what does the y value become? The y value shoots off to infinity. So we can at least describe what's going on in the situation, and just instead of saying, I don't know. Physicists do this a lot. Like you can imagine when people say, oh, what's the end of the universe? And the physicists can say it's ever expanding. They don't just have to say, I don't know, it's undefined. Or what does it look like at the center of a black hole? Like the math can be talked about in this way of a limit of what should it look like? Like what could we expect? The limit on the left side, as x approaches 0 from the negative left side, 1 over x. And this describes us walking on the left side as we get closer to 0. What happens to our y value? Our y value starts heading toward negative infinity. So the basic idea here is, again, saying what should it look like? Where is it taking me? Now, if I actually needed to calculate it, like what if I didn't know what the graph looked like? Well, you could plug in values into your calculator. Now, if I had a calculator, you guys can do this some other time. But when it comes to limits, you can always just plug in a number. If I plug in, let's just do a guess and check. Or just a guess, yeah, and check. I can plug in a number that's really close to 0 from the right-hand side. So I would plug in, for instance, a number like 0.001. Okay? That's 1,000th. And this would give me 1,000. If I plug in 1 over 0.0001, as I'm getting closer, see this getting closer to 0, the number gets even bigger. And that kind of gives me a trend. The trend is that I'm getting closer to infinity. If I want to approach from the left-hand side, 0.01 or 001, from the negative side, right? These are all negative numbers here. This would just become negative 1,000. And 1 over negative 0.0001. That would give me negative 10,000. So even if you don't know what the graph looks like, you can always plug in a number that's close, and it'll give you the trend if the value doesn't actually calculate. Again, if I had tried plugging 1 over 0, this is undefined. And in actuality, the answer is infinity. Now, let's talk about why the answer is infinity. If we talk about division in general, in division, we say A over B. How many times how many B's are in A? How many B's are in A? How many times does B fit into A? A simple example, 4 divided by 2. How many 2's are in 4? There are 2. How many 3's are in 9? There are 3. How many, we can think of this as money, how many dimes are in 1? Well, there are 10 dimes. How many pennies are in $1? There are 100. How many thousandths are in $1? Well, there's 1,000 pieces, right? So as a number gets progressively closer to 0, this number gets larger. Now, let's talk about this in another way, in an illustrative way. Imagine if I'm trying to slice a piece of cake, and I ask people, how much cake do you want? So someone tells me, I want half the cake. I want a slice the size of half the cake. So here's my cake. And the person asked me for half a slice of cake, half the cake. So how many slices do we end up with? We only end up with 2 slices. Because you asked me for half the cake, right? How many halves are in a whole? There are 2 halves in a whole. What if someone asked me instead, they want a quarter? Oops, lost that one. They want a quarter. So how many quarters are in a whole? There are 4 quarters in a whole. Of course, you can do this algebraically, like multiplying by the reciprocal. Okay? How many tenths are in a whole? There are 10. How many hundredths are in a whole? So eventually, we get to a point where, what if I ask you, how many zeros are in a whole? What if I ask you for a cake slice of 0? Do you want cake? No, I'm good. So if I give you a cake slice of 0, how much cake, how many slices can I come up with if the cake slice is 0? An infinite amount. I would never run out of cake. Everyone could get cake. If I take a slice of air and I give everyone a slice of air, hey, I can give air to everyone. And the point is that the reason why this is undefined, because this isn't a number. Infinity is not a number. So we can't say, oh, 4. So really a number divided by 0 is actually infinity in essence. That's why it's undefined. That's why we can't use it in our calculations. And in this case, you look here, it actually could have been positive infinity or negative infinity, depending on which side of the problem you came in from. So that's one of the reasons why we can't use undefined, because if I ask you for an answer and you tell me infinity, that doesn't mean anything to us. But in limits, we can use infinity as a term of direction. Like, where is it going? Well, it's heading off to infinity. If I ask you, what is the limit as x approaches infinity of e to the x? Now, let's describe this graph as an exponential graph that goes shoots off to infinity. So as x approaches infinity, right, and this is x going to infinity, what happens to the y value? The y value itself shoots up to infinity. But if I spin this around and ask you a different limit, as x approaches negative infinity of e to the x, looking at the graph that we have here, as x approaches negative infinity, the y value actually starts to shrink. It gets closer and closer to 0. Now, there's a couple of problems with this graph e to the x. First, could I actually plug in numbers that get me to infinity? No, you would never be able to plug in a number that got you to infinity. a million, a trillion, a billion. That will give you a large number, but it wouldn't give you infinity. So again, the idea of a limit helps me describe that situation. Or I say, what if I wanted to go to infinity? What would the graph look like? Or what would the value look like? If I went to negative infinity, this graph would go to 0. And the thing is, this graph actually never touches 0. It will never die. It's almost like the fly in your house that you swat that gets right back up and it's still there. It never dies. But what would it look like? And that's the cool thing about limits. It's not about what it is, because we did what it is in Algebra 1. This is what it should look like if we could ever get there. And it's unfortunately a little like higher concept here. So let's go ahead and talk about some practical limits, some limits that we can calculate. So the idea of limit is, again, what should it look like? Now, if I ask you the limit as x approaches 3 of 5x plus 2. 5x plus 2, what would the graph look like at x approaches 3? Well, if I went ahead and, this is kind of lame, but let's just try it. What if I plug in f at 2.9 and f at 3.1? What would the graph look like if I plug in those numbers? I might get a calculator on the side here, so I don't waste any time there. Oops. Oh, shoot, I'll just use my phone. Okay, so if I take 2.9 times 5 and then plus 2, I'm getting 16.5. On my right side, if I plug in 3.1, I'm getting 17.5. Okay, what if I get even closer? F at 2.99 and F at 3.01. 2.99 times 5. We're at 16.95 on my right side. I'm getting 17.05. Let's do one more. 999 and F at 3.001. 2.999 times 5 plus 2. That's 16.995. 3.001 times 17. Whoops. 3.001 times 5. And then plus 2. Oops. 3.00. Being 17.005. So you guys hopefully are seeing a pattern here just with these numbers. The next one is probably going to be 16.9995, 17.0005, so on and so forth. Now, so on the left side, 2.9999999, what do you think the number is getting closer to? That looks like 17. On the right side, the limit looks like it's getting also closer to, tough one, 17. So does the left limit and right limit agree? Let's go ahead and write that. The limit as x approaches 3 from the left side of 5x plus 2, this looks like it's going to be 17. The limit as x approaches 3 from the right side of 5x plus 2, this also looks like it's going to be 17. I wonder what the graph looks like as x approaches 3. It's going to be 17. The left side said 17. The right side said 17. But Mr. Ko, couldn't you have just plugged in 3? Yeah, you could just plug in 3. And that gives us 17. The point is that the world that we live in is defined by numbers and is defined by ideas like before we even learned it. Like it's already based in this fact of limits have always been there. As you get close to a number, does it really equal to the number that you're at? You know what, for Algebra 1 problems, for sure, yeah. If I look here, 5x plus 2, if I plug in 3, I get, 17. 17 that we were expecting. Now, limits 99% of all the functions you have in the world are always going to just be a plug-in problem, what we call a direct substitution. So this is what you should always do with limits. Just plug it in. Just try it. Always just plug in the value and see what happens. Because for most functions, they're what we call continuous. There are no breaks in the graph. So let's look at a function that doesn't work. And let's do the limit as x approaches, let's do 3 of, oh no, that's an easy one. Let's do 0. And we'll say it's going to be x squared plus x over x. Okay. So if we followed our previous rule and we said, that's just plug it in and see what happens. 0 squared plus 0 over 0 is undefined. Not only is it undefined, it's 0 over 0, which means for us, it's a special term that's called indeterminate. Indeterminate means in English, you can't determine it. So find another way. And that's one of the cool things about indeterminate problems is that it gives us a hint that there, you know what, it's probably going to be another way. We just have to figure out which method we're going to use to find that other way. And in this case, since it is a rational function, where it's like a polynomial on top and polynomial on bottom, it's probably going to divide out. That means someplace along the way, there is a 0 over 0 in whatever problem that's left over. There is a 0 over 0 someplace. So that's fine what that 0 over 0 is. So our first type of rational problems are problems in which we might be able to factor and simplify first before we then plug in using direct substitution. Okay, we're going to simplify first, maybe using factoring, maybe using long division, one of the tools we learned in pre-calculus, and then we're going to try again. If she turns you down once, think about a different plan and try again. Okay. So here we go. First move, I'm going to rewrite the problem. You must write limit because you have not plugged in the limit yet. Now, if you look at the top, I see x squared and x. I see maybe I can factor out an x. So if I factor out an x, we are left over with x plus 1 over x. I want you guys to make sure that is correct. X times x is x squared, and x times 1 is x. I'm just factoring the problem. And now we realize that I can divide out those x's. Now, here is also the big takeaway. I found the zeros. I found the losers. If I plug in 0 here, that's where we got our indeterminate from. We found there 2 zeros. Since we did that, let's go ahead and rewrite it. The limit as x approaches 0 of what's left over is just x plus 1. We can follow up with now plugging 0. Now, I've done this before, where if I plug in the limit, I do not write limit anymore. I am not going to write limit anymore when I plug in my limit. The answer is 1. The graph will look like 1. Now, is this what the graph really is? Okay, not what it should look like. Is it what the graph really is? No. If I plug in f at 0, the answer is not going to be 1. It will be undefined. And we did that. We showed that up here. We show that if I plug in 0, the answer is undefined. So what does the limit give me? It gives me what it should look like. And in many cases, if you guys remember, this is what we call the whole. If you remember in pre-calculus and in algebra 2, if we divide some variables out and we plug it back in, that is the value of the whole. The whole, you could say, this is just as a repeat, at 0, the whole happens at 0, 1. If I plug in 0, we have a whole at 1. Now, if you wanted to verify this, you could have plugged in f at negative 0.001 and f at 0.001. Negative 0.001 is really close to 0. F at 0.001, that's really close to 0. I'm going to go ahead on my calculator and plug that in. 0.0001. No, so whoops, too many zeros. 0.001 squared plus 0.001. Divide that by 0.001. I ended up with the answer on the right side as 1.001. On my left side, I'm going to plug that in. 0.001 squared plus negative 0.001. Oops. 0.001 squared plus 0.001 negative. Divide this by 0.001. We end up with 0.999. So I manually plugged in values that were close to 0. Now look at the results. What does 0.999 and 1.001 look like? Don't they pretty much look like 1? So our idea here is that the graph, whatever the graph may look like, but at 0, oh darn it, it's messing up. But at 0, we have one side at 0.9999. On the other side, we have it at 0.001. And at 0, we have a big fat hole. And if you guys remember your pre-calc, something kind of cool, this was your graph up here. The graph of the line is, the y-intercept is 1 with a slope of 1 over 1. Y is equal to x plus 1, except x cannot be 0 because the graph doesn't work at 0. So that's one of our ways of solving for limits. If I get 0 over 0 and indeterminate, our first thing to do is go ahead and factor if possible, and then try again. Factor if possible, then try again. Okay, I'm going to pause for just a moment. So if I give you the next problem is very similar. If I say the limit as x approaches 2 of x squared minus 4 over x minus 2. Okay. So my first step, just try plugging it in. Give it a shot. Why not? If I plug it in, we end up with 2 squared minus 4 over 2 minus 2. Again, remember, I do not write limit because once I plug it in, I've used up the limit. So that's 4 minus 4 and 2 minus 2, and we're left with 0 over 0. This is indeterminate. That means find another way. So we go ahead. The limit as x approaches 2. Remember, I haven't plugged in the limit now. I'm just rewriting it first. X plus 2, x minus 2 over x minus 2. Do you guys see the 0 over 0? See, I found you, sucker. You're my 0, and you're my 0. And if we got rid of them, by simplifying, our problem, what we're left with is the limit as x minus 2, x approaches 2 of just x plus 2. This is very, 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 very similar to what we did with holes. It's just another way of describing that hole, essentially. And now we can plug it in. When I plug it in, I do not write limit anymore. And the graph looks like it should be 4 there. Is it really there? No. The idea of a limit is this is what it should look like there. The actual value at 2 is undefined because we divided by 0.
Basically, x can't be 2 at all.
So if I give you a problem like this with x approaching -5 of a square root problem, well, just to graph this for you, this is what a square root graph looks like. And the graph does not exist on the left side because we can't take a square root of a negative. So just to add that, could I even use -5 then? Does a graph even exist there? No. So there's no answer. This is no limit. No limit. There is no answer to this. So if it doesn't work in a regular algebra problem, it won't work in a limit problem. So our expectations of stuff that works is still taken to our consideration of limits. If it doesn't work in the real world, it won't work with limits. So you can't divide by 0. You can't take a square root of a negative. So be aware of that. So substitution doesn't always work. So we have to find other ways. Like if I give you a problem that says limit as x goes to 3 of 1 over x minus 3. If I plug in 3, we end up with 1 over 3 minus 3. Now, this leads us to 1 over 0. Is this indeterminate? It's not, because it has to be 0 over 0. So since it's not indeterminate, the answer is no limit. Please be okay with saying no limit when something doesn't become 0 over 0. For us, if it's a rational problem, a fraction problem, if it's not 0 over 0, the answer is that. If I give you a problem that says limit as x goes to 3, let's use another number so you guys aren't confused. Let's use 4. And we'll say it's going to be x minus 4 over 4. First method, go ahead and plug it in and see what happens. 4 minus 4 over 4. As you remember, I do not write limit because I plugged it in. Well, that's 0 over 4. What's 0 divided by 4? That's not undefined. That's not a number that doesn't exist. That's 0. And actually, this is our limit. That's our answer. If the answer is 0, that's what it is. How much money do you have in your bank account? 0. That doesn't exist. No, you have 0. You're broke. It's not undefined. It's not indeterminate. Oh, I'm just waiting for it to be determined. No, you are broke. 0 is a wonderful answer, and it is a point that we can graph. So if it's a number over 0, no limit. That doesn't make any sense. If the answer is 0 over a number, that's just 0, and that's 100% okay. Kids get confused because we start saying you can't divide by 0, and all of a sudden, kids don't know how to use the number 0 anymore. 0 is an okay number if 0 is on top. 0 is not an okay answer if 0 is on bottom. Okay. I'm gonna stop here.